Welcome, San Diego C Meetup number 62. Uh, we have a very interesting session and few surprises and raffles and giveaways. So more details soon. Um, if you are a new member, please feel free to approach me if you want to have any session. It's a good experience to get some domain, prepare a few slides. You always get a lot of knowledge out of such exercise. So I highly recommend to do that. And we are very casual. Like, this is nothing official here. We are all friends, and no judgment and all. Just we want to share information and knowledge. That's the whole idea here. So welcome if you're new. We are just meeting every month to discuss C++ topics. So I have a C++ quiz just to warm up things, and then I'm going to have a single chapter from the new book from Marius. We'll talk about Marius in a second. Modern C++ Programming Cookbook. This is the third edition. I pretty much read the first and the second one, and Marius is one of my favorite authors. He published a lot on Packet. He has multiple books in C++. He also has at least one on C Sharp, but we are focused on the C++ part. So highly recommend to look at this book. We'll talk about it in a second, and also the other books that he has in Packet. The meetup fees are paid by the Qualcomm Cloud AI BU. I'm part of the group. Though I'm a Qualcomm employee, it's not sponsored or affiliated or anything like that from Qualcomm. This is pretty much my own thing, and just kind enough to reimburse me on the meetup fees. It's about $100 every 6 months. We have Dropbox link where I'll place the PowerPoint slides, and YouTube channel would be populated with the uploaded session as soon as I can after the meeting. Twitter, just to be aware of the announcements and all. SDCPP meetup. I have Kobe_CA, and we also have a Discord channel that we mostly I'm using for announcements, but no more than that. My name is Kobe. You can find CPP Cast, a couple episodes, and I was reviewing Dorothy's book some time back, which is, I think, was a great book from Dorothy about object-oriented with modern C++. Okay, so I'll pause for a second. We are encouraging people to use this platform to announce on any position. So I'll let Bing Long to and just use this spot to have his slide. So Bing Long, go ahead.
Thank you, Kobe, for this opportunity. So I'm here to share the job opening here at Apple. So as you know, Apple has huge site now at San Diego, actually multiple sites in San Diego, and we're looking for a C++ programmer. The position is in a bigger computer vision organization in Apple. We have algorithms shipped on Apple Vision Pro and similar products. So we're not looking for an algorithm expert for computer vision, but we're looking for a generalist. You should be a passionate modern C++ programmer. We believe in modern C++ for the performance and abstraction power. So the ideal candidates should believe in the same way. Okay. So feel free to contact me through LinkedIn or my email. That's my full name at apple.com. I will try to join the Discord channel. I haven't. So okay. You could probably also find me there.
Yeah, use the meetup or maybe IM me through Twitter or like x.com. If you need an updated, because the invite link would expire every so often, so just let me know if you need the invite. I'll post it. I'm trying every time someone is asking it. I'm using the Meetup platform to post the new link. So feel free to just catch me after the meeting, and I'll send you the link.
And if you know your friends, whatever, social media, whatever network, and you find good candidates, please help to recommend them to me. So thank you very much.
Thanks. Yeah, great opportunity for you all. Always uh, would like the C++ community here in San Diego and outside of San Diego to expand. Okay,
Thank you.
so yeah, you're welcome. So I have two of these quiz just to have a nice warm up before we go to the main thing. Let's just use just one. So I'm going to stop sharing and reshare. So give me a sec. Okay. Hopefully the fonts are big enough. So uh, we have this main function, and it is bringing string literals and two strings constructed. And what is the output? If there is an output, is it compilation error, undefined behavior, or unspecified, or implementation defined? So take a moment to take a look at that. It's very confusing. You need to remember, which I don't, by the way. I needed to go and take a look at the constructors of stud string. It is somehow the idea behind this question is that you at least be aware that things behave differently with different argument passed to the constructors. So it's different constructors. If you can remember, and I can't remember, by the way, I have also always CPP reference in one of the tabs to I can memorize millions of constructors and millions of APIs from C++, especially when it's expanding more and more. So CPP reference is always open in one of my tabs. So the first one, 5. So the idea is that the 5 here, five in the first one and 5 in the second one, they mean two different things. One is the first one means count. The second one means position. so uh, so given this, so the second one, by the way, it's a string because of the string literal versus const pointer. So string literal, this hello world is actually a string. So it's constructing hello, constructing a string, and the second parameter of this constructor is a position to construct to start from. So it's basically should be hello world, because S1 and S2 are two different things. So this basically provides the full details of why why it is what it is. Again, the whole point is few reasons. One is to confuse us. The second one is to demonstrate how like things can behave differently. Just one single character change the way it's being constructed. So two different constructors. So this is a construct pointer and then string. Uh, Take a look at this one. Position. Construct an object of basic string and determine the effective length. The initial string value as str size minus position. So that's unfortunately this is confusing, but I'm just a messenger here. Okay, so let's go back to the main thing. Gonna reshare it. Okay, so I wanted to just introduce Marius. He's not here. He's on a very different time zone in Europe. I think Eastern Europe, if I'm not mistaken. And I, as I mentioned, I'm following him. He has great work. I just want to highlight also the template meta programming with C++ and the modern C++ challenge. Two books very similar in the concept to actually the modern C++ challenge is similar to the modern C++ programming cookbook. Lots of chapters with a lot of information. What I really like from this kind of books is the ability to absorb a lot of information and a lot of techniques that are very hard to find otherwise in traditional books where you just teach you C++ from from scratch. It's usually in the beginning. This is can be very advanced in terms of the topics. The template meta programming with C++ is starting with basics maybe, but it goes into a more advanced topics in templates and meta programming towards the two-thirds of the book. So highly recommend both of them. Now, we are going to talk about the Modern C++ Programming Cookbook, third edition, which is recently published. And let's do this. I have from the publisher three, as far as I remember, three PDFs, coupons that I would like to give away. So just email, not email, sorry, just ping me in Discord, and I'm just gonna pick the first three that that I'm going that I'll see in my inbox. So just ping me on Discord. I'll hand it off to you when so I need your name and your email to pass to Packet so they can send you the PDF that would be on your name. Um, Another thing, which I don't have a slide here, but it's a good opportunity to mention. I also have a um, coupons to give away for Sea Lion. I think it's 1 year free subscription. So I think I have couple, and we'll have more towards the future meetups session. So uh, so about five people, three would get the book, another two would get Sea Lion. Let me know what you prefer. So I'll just pick the first three for the book and the first two for the Sea Lion one. Sea Lion is my preferred IDE. I really like this editor and what it brings to my development environment. Uh, so I would recommend that uh, a lot. So that's another thing that reminded me. Okay, so let's take a look at the actual book. So the book has many topics. I just enumerated few using scoped enumeration, which is the new one from 20, or maybe 23 even. Multi-dimension op. The book is actually 23, which is, I had it somewhere. I had the book actually somewhere. Yeah, so it's 23. So a lot of 23 things in the book. So worth looking at. So just listed all of them, and it's a great resource. So if you have a chance to take a look, it also talks about coroutines, generators, which introduced in C++ 23. If you remember, coroutines are introduced in 20, but they were like the bare bones ones, and 23 and above provided more kind of high level blocks to be used. Generators is one of them. So I took part of chapter 3, just part of it. It's a big chapter talking about high order functions, map and fold. Reason being, I really like this topic. It is a great opportunity to uh, uh, talk about templates, uh, compositions of functions, and it actually it opens our mind into some very interesting domains where you can do a lot of things with functions, which behaves like a first class citizens, which is really nice. So if you're coming from functional programming, this is something that you would appreciate a lot. And uh, basically C++ is a multi-paradigm language, so this is just one aspect, which I really like, by the way. So we'll start with implementing high order functions, map and fold. This should, by the way, this whole session should be, I believe, until 6 p.m., like my time, another 40 minutes. Okay, so in C++, some of the terminology of high order functions and things that you might be familiar with from different languages are a bit different in the way they are uh, used. Uh, if you're really interested in how different languages use different naming for this type of functions, I recommend you following Cornell Orchestra, which is has multiple uh, talks and websites, and he is very enthusiastic about that, and he has a lot of comparisons about like how each language behaves, or what is the naming of each of them. We're just talking about subset here. Transform basically is a map. Accumulate, std accumulate is basically a reduce or fold. Um, Basically, if you think about high order function, it's something that takes a range and arguments and just apply them to the range that we pass. So a range can be anything like list, vector, map, anything that behaves like something that we can iterate over. Um, Map and fold that we'll take a look at would return new range. So we always have a, a range passed and a range uh, being passed back. We're going to apply function. We're going to pass a function. We're going to apply the function to the elements. Uh, Fold is basically taking the range and reduce it into a single result. So this is basically reducing it. We'll talk about fold left and fold right, and we're going to also explain how that is behaving. How does it behave with respect to fold expressions that you might be familiar with from C++. So here's the first code. We'll have a lot of code snippets, so this is one of them. Uh, so std transform is something that you might be very familiar with, that takes a range, begin and end, and then another range to basically kind of an output one. This is uh, what we use here. It's the same range. So we actually passing a range and returning a range while applying a specific function. I'm not going to talk about std forward. Uh, it's just I imagine that we actually maintaining the same uh, value category of the function, and just pass that to the parameter that takes the function. We apply this function for every single element of the range, passing into the range itself. So basically, we're overriding each and every element on the range. We're not going to talk about parallel uh, transformation or parallel reduce in this session. That's a different whole discussion. So we are not covering that here. And I don't remember if I can't remember if the book itself is covering parallel one. So this is basically an overload that takes std map and another overload that takes a std queue. So we're basically going to have three different overloads. The reason being that this is a very generic one where there is a way to iterate over the range. Stud map might be a different, need a different kind of treatment, including stud q. If you think about stud q, the way to iterate over stud q is the way it's written here. Let's see if I can. Well, while it's not empty, you take the front, apply the function, and push it into this R, which is the one that we're going to return back from this function. So so that's the Q1. Stud map, same idea. We have the map that we're going to return, iterating over the range, which is M, which is the map here, and the key value pair is being passed to the function. Something is returned, and we insert that back to the map. So key value pair passed, key value pair is returned, and we insert that. So these are the special treatment that we need to have. So that's something that you might need to consider when you build a library that needs to deal or to, might be used in with multiple types of containers. So let's talk about fold. Stud accumulate is something that you might be very familiar with. Again, it has a range, an init value, and a function. Again, we use stud forward f to keep the value category of the function. Just ignore it for this session. And accumulate basically is a reduce. So we are iterating from the left. So basically just taking every single element and applying a function that takes whatever we accumulated so far. When I say accumulate, it's maybe accumulate, it's not the right. Whatever we have, the single value that we have so far, and apply a function on the new value, reducing it to a single value. Eventually, you'll have a single value. Function can be plus, can be any, like can be multiplication, can be anything that takes the value so far and a new item from the range, apply a function, and returns a single value, and we use a single value for the next iteration. Fold right is an R begin and R end. It's basically the same idea, but we use R begin and R end so we can fold right. That's basically the idea. Just like we mentioned with the stud map and stud q, you would need to apply something similar with q, passing an init, having a function with an init, and the q front, and then popping it and returning the single value that was we reduced the whole q into a single value. So that's basically the idea here. Now, when I was reading the chapter, I couldn't not refer into the fold expression that we have since 17. So fold expressions would, if this is the first time you're hearing about it, so there is a very good explanation in CPP reference. So you have a pack op and then dot, which means, just repeat that. A right fold would have this specific I don't know if you can see, yeah, I can see my cursor, would look like that, and this is how it's being interpreted. The left fold would be would have this syntax, and it's going to interpret it like that. And it's really important in some operations. Some operation doesn't really matter, but in some operation, whether you're doing right fold or left fold, and there's also an init variation. So you can see that a right fold with an init would look like that. The E1 would have operation of the rest, operation with the rest, all the way to the N one that has the init, versus the left fold would first have the init and then operation with E2 operation all the way to So that's basically it. So when I looked at the chapter, I couldn't not making this comparison between these two. So just bear in mind, we'll take a look at that towards the end. Fold left, fold right that we show here are not really the same as fold expression. The fold, and I had a discussion with Marius on that just to follow my own clarification. Fold left and fold right, although they sound like fold expression, they're not fold expressions. They basically a way to iterate either from the left or from the right. From the right would be our begin, from the left just begin and end. So just bear that in mind. We'll mention that another couple of times throughout this session. So how do we use these overloads? So let's take a few examples. And when you have an opportunity in your either hobby project or day work to use that, just remember that this is a very good opportunity for you to generalize your code if you need to uh, maybe use the building blocks of the standard library, but you can always build something on top. Uh, it's been more than a few times in my project that we needed something slightly different from the standard libraries algorithm. So we build on top of what we had using something very similar to what we see here on the slides. So it's more than theory. It's actually a good thing to remember and bear in mind. And obviously the book has many other examples, much more than I have here in the slide deck. Okay, so here's an example of map F, which is basically takes, if you remember, it takes a function and a range. The nice part here is that just like ranges, either the standard library ranges or ranges v3, we don't need to deal with begin and end. We can pass the range itself, the rangeable uh, container itself, and that's it. So mapf would do std begin and std end as needed. So this is the absolute. So we have these values returning r. So r would have 0, 2, 3, just having the absolute values. That's basically a very easy example of how to use mapf. And if you want to go back to mapf, so this is basically how mapf is defined: a function, a range, and we're just running std transform. So basically, from a range, we're getting another range. So we're mapping one range to another range, applying some transformation on each element. Yeah, one thing to remember is that it is sometimes a good practice to take this lambda outside. It really depends on the use case. Getting it outside of mapf and naming it something uh, meaningful, maybe also can be reusable later in the same scope. So we can think about it as another option beside what you have here on the screen. By the way, stop me if you have any questions. Here's another example. We're using list. We're completely agnostic. We have three overloads. We're completely agnostic to what kind of uh, uh, container we have. If people are very familiar with or somehow familiar with concept, we don't use concept here in this session, though. If you have the book, you'll find it there. But concept can validate some assumptions. For example, that we have something that we can iterate over and so on and so forth. This is just basically taking each element and multiplying with itself. So this is the result. So very generic, very useful. Think about it when you write code and you want to have something that might be reusable for others. So here's another example, a bit more involved. here we opt into, instead of having lambda, which is perfectly fine, we're using a function object of functor, uh, what we used to call functor a long time ago. Uh, it helps if I want to uh, specify a specific uh, overloads, because if you look at how stood round define, there are multiple overloads. Let's say I want to have double as the default. I can have uh, f round that just calls stood round with the value, whatever it is instantiated with. We have a default here. This is why f round here is used with this funny template syntax. It basically means just pick the default, which is double. Amounts is a stood array. Again, it's something that we can iterate over. This is how these are the results of f round using stood round of double, because value is type of t, which is double. So that's another option. Uh, there is an enable if t here that could be transformed into a, or used with concept instead of enable if. But at that point, uh, chapter 3, I don't think concepts are introduced. So enable if t is basically a simple facility. It's not really simple. Well, it's simple, but if you're not familiar with it, might be a bit overwhelming. Is floating point v would return true or false. If it is true, this would yield whatever is after the comma, which is t. Otherwise, it yields something that would fail. This is what the sphena is. Substitution is failure is not an error. So basically, if you try to do something which is not a floating point, for example, if I do f round of int, I wouldn't be able to use, there wouldn't be operator paren, which is basically a callable operator, defined. So we'll get an error. Might be a bit of overwhelming error, depends on the compiler, but I don't think it's going to be a short error, in my opinion. I haven't tried it, by the way, but usually it's not a simple error. This is why concept should improve it, though. What I'm hearing more and more, it's not really improving it a lot. I'm not using C++ 20 enough to tell you that this is true, but I hear that it's not really solving this problem. So this is the F1, this is the stood round that I mentioned. Okay, let's try another example to use the same idea. So right now we're using stood map. String is the key, int is the value, and we just initialize 1, 2, and 3. We pass a lambda and we pass the words, which are the containers, and applying the map to upper. To upper is a function, and we taking the key value pair and using the first, returning another pair. So basically, what you see here are two instances of mapf that we start. This is where we start composing or combining more than one mapf, which is perfectly fine. The idea here is that we iterate over the items. For each key value pair, we're returning something. We're returning a pair. But how do we do that? The value is the same. So this is why 1, 2, and 3 is the same. But the key has another transformation. To upper is a function. First is basically another element that you can iterate over. So it's an array of characters that you iterate, and we just run to upper for each of them. By the way, anyone think that this could be maybe a different signature? What do you think? Maybe a const reference and a const string, because usually the stud string sorry, the pair that is being passed, it's a const key, comma, value. So you either using auto, let the compiler use the right stud pair, const key, and comma value, or you do it yourself if you're familiar with how this is being passed. But basically, it is better to have a const stud string, or just use auto, and then key value pair would still have first and second. So this is where we start combining functions. You can make same deal. You can name them if you want, and then there's some work to be done to be passed internally, but that's pretty much trivial to do. But that's also very kind of kosher to do that. Okay, Q is another element that we have overloads. So priorities, we have 10, 23, 30, 40, and 50. We normalize it. So everything that is above 30 would get the number 2, just normalizing it like in some way. Anything else would be 1. So 10 and 20 would be 1. The rest, sorry, 10, 20, and 30 would be 1, and the rest, 40 and 50, would be 2. This is a way to normalize it. This would be picking the map F that has the overloads that takes Q. Again, we as users, we don't really care as long as the author of the library that we use did a good job in applying the right overload, so we can use it, because Q behaves a bit different from other containers. Okay, how about using fold? So I need to have these 2 quick recap slides just to refresh your memory. Fold left, fold right. One is begin, one is our begin, our end, but they have the same idea. We take a range and we reduce it into a single element, applying. We have a binary function that takes the value so far and the next element, applying a function, a binary function. Accumulate is really common to use with that, but there are other functions in the standard library that are providing this similar, though they have some subtleties on what each can do. We use accumulate just because it's very convenient. Remember that we're not really talking about fold expressions, and towards the end of the deck, I'll explain where this is different versus fold expressions. Okay, so let's take some examples and see how we can apply fold left and right on each of them. So the first one, so we have a vector of integers, the vector of numbers. So remember, we have the function, the range, it's a vector in this case, and some init value. And what we do here is the sum. We have a sum so far, and then the next element. So we're reducing that to s plus n. So you can write it yourself, but always remember that at least for few of the functions, the standard library provides some defaults or some functions that you can use. Stud plus is one of them, so we could just use the same code, but stud plus instead. We don't need to reinvent the wheel. Fold right would do the same. Why? Because adding 0 plus 2 plus minus 3 plus 5 and so on and so forth is the same as 9 plus minus 4 and so on and so forth. So they'll produce the exact same number. It's not always true. It depends. In this case, it is going to provide the same value. But it's not only numbers. If you have something that works with the function that you provide, using plus here. Std string has an overload plus, so this works beautiful with std string. So I can actually concatenate strings very easily with using fold left or fold right. Now, fold right would provide something different. Fold left is very simple. I'll take hello. This is the string literal that I mentioned in the quiz, and then space word and then exclamation mark. We get hello world. If we do it from our begin, we take the exclamation mark, word, space, and hello. So in this case, different result in folding. So we take multiple strings and we eventually return a single one. Uh, just bear in mind that there is a cost on copying and allocating and all of that. So this is not free, but it's very nice introduction to the opportunity of using such technique. Obviously you need to measure and all. Just bear in mind that this is not really cheap. In by the way, in many cases, different since it's all templates, different templates would have different instantiations, so different things would have different uh, uh, code that is generated. How the optimizer is taking care of it and how it's inlining and all. You need to take a look at the generated code, but just bear in mind there's a lot of things happening behind the scenes when you read this code. But it's very nice on at least on the front end when you as a user using this library that was provided by others. So a nice way to have fold left of civic, which in this case would provide the same string back using plus. So yeah, since uh, we can take a string plus a character that works also. The init one is an empty string. This is a very nice trick to just use quote and then s and you're done. Obviously, you need to bring using namespace string literals in order to have that. By the way, there's a lot of literals in the standard. Chrono has literals and some others. So get yourself familiar with that. It might make sense to use it in a lot of use cases. Uh, here's another example. Here we just want to iterate over the map. Same idea here. Const stud string is probably more appropriate for the stud pair. If you don't want to deal with that, just have auto. Auto would be deduced with the right with the right type. What we want to do is do the fold, but we just want to take a look at the second of the pair. So we just want to accumulate whatever is the second one, starting from 0. So that's another way. The idea is very nice. You can take this map. It's gonna pick the right uh, overloads and and do it very transparent. So that's a very cool idea. Um, in this case, by the way, the generated code would be very like given that you're not making copies here with the const non-const reference. If you fix that and have a const stud string, you can avoid the copies and just have numbers that are being just uh, added to each other and just getting an integer back. So it should be very relatively cheap as if you had a for loop. But this is nicer than for loop, I think. Okay, let's take a look at more advanced topics. So here's where we combine plus another map and another map that is we're applying something. So we need to kind of unwrap it or unfold it from the innermost one to the outside. So in order to get that in uh, a more kind of easy to understand. So here's how it's being done. So first of all, we have a fold left of plus and something, uh, having uh, 0 as first. It's stud plus, which is the function, then some range and an init. So this some range, remember that map f is mapping a range to another range. So the idea here is that after this map are done, we're getting back a range. Okay, so how's that being done? Uh, so first of all, we have uh, an absolute. So if you I have the initial values, which is 0, 2, -3. We first have an absolute on them, on each of them. We get a range back. Remember, map f of a function and a range of vnums. So which has a map f of a function of vnums. This is basically the innermost one. So we get an absolute back. We get a range back. It's the same range, but now it's absolute. We now apply another transformation that takes each element and multiply with itself. This is, by the way, a mistake. It's I times I. Uh, and then and eventually we sum everything because this is a plus and get 236. So this is getting more complicated in the sense that it's a transformation over transformation. The idea here, just to not to confuse yourself, is map is always returning a range. So I'm applying something on a range, getting a range back. On the range that I've got back, I'm applying a function, got a range back, and then I'm doing a reduce with the stud plus. 0 is related to the final reduce. So it's a 0. It's a 0 plus 0 because we have a 0 here also as the first element. Okay, we can actually take that a notch higher by applying fold left as a variadic template. So here's an idea of how we do that. Basically, a fold left. So we have uh, one overload that takes just 2, and if it takes 2, just apply the function on the two argument or 2 parameters. And then we have one fold left that takes a function and more than 2. It can be 3. So the idea here is that it kills each and every first element. So it applies a function on head, comma, whatever the rest, and so on and so forth, until it gets to the last couple 2. When it gets to the last couple 2, it applies the transformation and then start unwinding all the way to an f that takes a head and a tail. A head and a tail would be this function, and everything is done. So that's basically how it's being used here as a fold left. This is why it was kind of confusing when I looked at fold left, because fold left is not really like fold expression is not really behaves the same as what you see here. Actually, let me take that here. So this is fold left. So fold left would be something operation applied on the next one, and then the result is applied on the next one, the result applied on the next one, and so on and so forth. This is fold expression left one. While what we see here is the head and then the rest, which is looks like a fold right expression. But this is so when I asked Marius like what his take about this at least my confusion, he told me don't think about fold expression, think about this is basically an operation that starts from left and continues all the way to the end of the range on the right. So this is the way. So it's kind of not really following the fold expression per se. There is a chapter or subchapter on fold expression, but this is something that basically confused me when I was reading that, and Marius helped me to uh, clear the confusion.
Quick question, Kobe.
Yeah,
So can we remove the first function as overload if we use if const expert in the
yeah,
function?
yeah, yeah. I believe so. Yeah,
Because
and
having more functions like a more clutter.
yeah,
Or
I think the idea behind this chapter was not to introduce a lot of the more advanced topics. I had the same thought when I was reading that. I decided to have that as is. Um, and obviously, his other book also discuss on these advanced topics. But yeah, there are more ways to improve that.
mm,
But if you have an opportunity to look at the book, uh, it is getting into the more advanced topics. So thanks for asking that. So fold left 1, 2, 3, 4, 5. Fold left is hello world exclamation mark. If it was fold expression, it would look a bit different. Error too few expressions because we have only one parameter and there is no overloads that takes one, like one argument beside the function. There is either head and the rest or args1 and args2. So I just wanted to, and I have a link to Godbolt, just to, if you're not convinced about what exactly happening with hello world exclamation mark. So uh, you have a plus of hello and fold of the function, which is plus, and the rest. And then you have this whatever left, which is the plus of empty, and then fold of plus and the rest. And then the remaining one would be word exclamation mark. So this is basically where the two argument function, and again, it can be improved, but the two argument function overloads take place. And then there is a space because we have a plus of whatever happened with the rest, and then plus of the hello, which is the head, and whatever left from the return of the function. So this is how the hello world is actually uh, built. So this is another way. Um, Composing function into a higher order function is pretty much very similar, but there are all kinds of concepts that you can use. And I think we mentioned that one of the maybe 2, 3, 4 years back in one of the sessions. So you can have a compose function that takes f and g, and you need the equal sign in order to bring the f and g into the actual the lambda internally. And what do we return here? Compose is actually basically returning a lambda. It's just returning a function. So this whole idea of first class citizens using functions first class citizen is a very interesting idea that you can see. It's not, once you get used to the syntax, it's not a terrible thing. So it returns a function that gets one parameter, apply g on this parameter, the results are returned from g, and we apply f on on the result. So here's how we can compose two different lambda, so f and g. We can see how we can improve it soon in a second. And I'm calling this, so remember, compose returns a function. So if it returns a function, I can call it. So this is where I call -3. So -3 would have, so we have g here, which is basically -3 times -3, and then we have f, which is toString. This is why v would be the type of string and would have 9 as a string. But we can actually improve it
Kobe,
further. Yeah.
quick question for the previous slide. So here, if we could remove the keyword return, like some other languages, the code would be much easier to read. Uh, show the intention, right? Right now, all this boilerplate is wasting our pausing time for our brain, right?
Yeah, but we're not in Rust, so it's not like I have this without the semicolon and I'm done. So yeah, we need the return.
Like
Uh,
this int const n could be auto x, and then return could be dropped. Just a an arrow x to
yeah,
x times
yeah.
x. That would be nice.
Yes, but again, this is what we have. Yeah, there is a question. Yeah,
Yeah, quick question. So in that compose function that you have there, why is it necessary to put a template type name F and G around it? Why not put auto in there directly?
yeah, yeah. I was looking for this question. Uh, I think I had the same question when I was reading. So the book is 23. So your question super valid. I think what the book was trying to achieve, and you can contact Marius. I can give you his contact number. Is super
Yeah,
super nice person. So I think he wanted to start uh, from pre 23, like maybe 17. So this is 14, right? This is 14. This looks like a 14 compliant code, not even seven, doesn't even need 17. Just auto polymorphic lambda is 14. I think just taking it in steps, but I had the same question.
yeah, no, because I've seen this pattern before in the compose done that way. But I looked at was it Hickstra or the Conroe Hickstra, and his you know combinator library. He's just using auto. He
Yeah,
doesn't use the
yeah,
template around it.
yeah. We
Yeah.
don't need it. We don't need it here. So
Okay.
auto,
Because auto should take care of it, right?
yeah, auto. So basically, almost almost went into 17. So having auto here and auto here was almost in 17. There are actually books, at least one that I know of, that I purchased maybe 7 years ago. That was book about 17, but it was written and closed before the standard was completed, and it actually had examples, and it was C 17 compliant book. Well,
Yeah.
and it had auto, and I remember it used to confuse me because uh no compiler could could actually compile it. It was like, how's that possible? Because I'm using a C 17 compliant compiler, and it could. So that was after C 17. I think it's just, I'm with you, especially after the other comment about the boilerplate code. That's definitely removing more boilerplate code. Why do we need the template here? Yeah, I totally agree.
Yeah. Thanks.
So yeah, so just bear in mind that if you pick up the book, the book would get into a more and more advanced topics. So it's a very interesting, but it takes you kind of in a some path of learning. Uh, so I can actually not have just two, not strict myself to two, but I can have a variadic template that compose it in multiple. So this is nice. I can have this compose function return passing -3. That's I'm calling the function absolute plus times to string would have 36. Um, this is another one having uh, a list of, it's a vector of numbers having the same idea of absolute, and then uh, plus, and so on and so forth. So I can do all kinds of compositions, having map f internally in each and every lambda. So it can be super wild. So this is my last slide for today. It's basically kind of combining a lot of information that you can, all kinds of craziness that you can do. Basically, you can think about overloading this operator uh, uh, in the way that I can actually uh, compose. So you can see this composition. Instead of calling a compose function, I can take a function and have the overloaded operator times in order to get something. Maybe depends on the person, might be a more uh, easy to read or grok. Instead of having a compose function, I'm having something times something times something. The idea behind operator overloading is that make sure that this is something that your user would not be confused. Usually users, they want, when they using an operator and you overload that, they expect to see the same behavior. I don't know if that's the case here, but it's just a demonstration that you can have this type of an overload. All the um, comments about having auto and all applies here as well. Um, and this is just a few example of how we can um, use, it's the same idea, just synthetic sugar of using this overload operator. Okay, so that was my last slide. Just on time. It's 3 minutes after 6. Uh, any questions?
I have a question, Kobe.
Yeah.
So you had an example in the middle that you generate a range from this high-level function, then pass it to next high-level function, high-order function, sorry. That means it would create an intermediate container.
Yeah.
And if we do enough, this kind of relaying, we are creating a lot of
Temporaries. Yeah. That's what I was saying. This is a nice introductory to ranges. There is a lot of improvements that you can do on top. Now, let me just bring a reference, and I can't remember the exact chapter, but there is a book that I recommend named Beautiful C++ that has a chapter that demonstrate lazy ranges. And it's a beautiful, there's a beautiful example. I can't remember the chapter, but if you just happen to have this book, either the printed one or I think it's from Inform IT website that you can purchase that. It has a nice example about how you can construct ranges which are computed lazily. So this is just an exercise, just to understand the opportunity. I think I mentioned that in one of the slides, that there's a temporaries. It's not, might not be as performant as you would expect because of the intermediate ones, especially when you return ranges. If you reduce, um, it's just it's just a single reduce. It's not a big deal, especially if you make it correct. With We had an integer example, so it's easy. It would be like a for loop, but yeah, be mindful to what happens behind the scenes. Uh, I think it's the same when I read code and I read such code. Like I'm um, very aware of how the parameters are being passed. What is the return value? Um, and I am aware of what are the intermediate uh, uh, values that are being generated. So I'm not going to take that into some critical path with like very big ranges. That's something that needs more work, but it's just a concept that you can start with. And again, take a look at the beautiful C++ book. It has one beautiful example of, sorry, I'm using the same beautiful C++. It has a very nice example on creating lazy ranges.
Yeah, I think there was some famous work in many years ago. It's called expression template. So it's basically remembering it's like a view into the original container, right? And then it constructs tree of operations, as long as you keep the same size, and it will only generate the lost container when you try to evaluate this expression. So you are constructing expression, it's a lazy representation, but it's returning some tree representation at the compile time. But if you say dot evaluate, and then it will do all the calculations
Yeah.
specified.
Yeah. There's a chain reaction that happens. Yeah.
Yep.
Yeah. Yeah. It I remember when I was reading this chapter that had that explained, I needed to really like just to concentrate on the examples, because it's a very unique one. So it's worth looking at. Yeah,
Yep.
thanks for bringing it up.
And they do have limitations as well.
Yeah, of course.
There's an evaluation because it's keeping some references to the
Right?
other.
They need to leave. The reference need to leave.
Yeah,
So
you got undefined.
you have lifetime considerations in that, because as you mentioned, it's all about keeping the references. Yeah. I'm not saying C++ is easy, by the way. That's not what I was. That's not what I'm saying. It's not easy. Okay. Okay. Thanks everyone. Thanks for joining me. See you next time. June. Take care.
Thank you, Kobe.
Thanks. Take care. Bye.
Thank you.
Bye.
Thank you.
Thanks.
Thank you.
Thank you, Kobe. And good night.
Good night. Good night.